All right. All right, let's just start. Then other people come, they can join us halfway. Actually, let me start the slideshow. All right. Do I see a full screen? Okay. All right. So today we're gonna be talking about flip. All right. I'm gonna be talking about gases. Do you guys have any idea what the blue is? All right. I have a periodic table here. What's the blue part? You know, take a guess. And you guys can type in chat if you guys don't want to talk. I mean, type in chat. Give me a guess. What is the blue part? You know, gas. Yes, gas. How surprising, right? We're talking about gases. Yep. So the blue part are gases, and they're actually gases under standard conditions, because gases, they don't always stay as a gas. These just happen to be gas at room temperature. So that's well, it's supposed to be like 25 degrees, but well, we live in California. And that's that. But room temperature and also pressure at sea level, all right? Because pressure has an effect on how much, or like, yeah, pressure has an effect on what state of matter it is. So we're talking about very normal conditions, all right? All right. So next slide. Okay. All right, so we'll be focusing generally on the behavior of substances that exist as gases under the normal atmospheric conditions, which are defined as 25 degrees Celsius and 1 atmosphere of pressure. All right, so notice that hydrogen, nitrogen, oxygen, fluorine, and chlorine exist as gaseous diatomic molecules. So when they're as a gas, oh yeah, they have two of them. All right. I think we talked about some of this last time. So yeah, some of them stay as diatomic. So it's a good idea to memorize these. It's not that hard. Cl and F, and actually these two as well, Br and I, when they're gases. Nitrogen, oxygen, these two, memorize them. Hydrogen, memorize them. But yeah, the good thing is they're mostly in this area, right? All right, these two, and then this column right here. So yeah, it shouldn't be too bad. All right, now an allotrope of oxygen, which you might have heard of, ozone. The ozone layer, the one that we pop the big hole in, all right, trying to fix it. That's why you can't spray, aerosols anymore. You're gonna poke a big hole through the ozone layer. But the ozone is also a gas at room temperature. Yeah, it's basically instead of 2 oxygens, you have 3 stuck together. All right. So all the elements in group 8A, are known as noble gases. All right, I think yeah we talked about them. Remember the octet thing that doesn't really exist. The octet rule. Well, anyways, they're noble. All right, they're noble gases. Why are they called noble gases? Well, probably because they're all gases. So yeah, just look on the periodic table. Honestly, this rule, don't memorize them. Just look on the periodic table. All right. So yeah, when you're doing your test, turn around. There's literally a big, really huge one on the back of the room. Turn around, you'll see it. All right. Now, ionic compounds. They don't exist as gases at room temperature. Why? Because as we talked about last time, well, or I don't know if it's last time, but we talked about this before. But ionic compounds are actually held really tightly. I think I talked about this, that they need like thousands of degrees, right, to melt and to, if you want to boil it, then that's like even higher, right? So they don't really become gases at room temperature, as you might guess. So yeah, under normal conditions, all we can do is melt the solid. All right. So as you can see, salt, right? The salt you eat, that melts at 801 degrees Celsius. But good luck getting gas. All right. Gonna boil it. It's well over 1,000 degrees. Try getting the gas. You're not gonna. All right. So some molecular compounds are more varied, which means that they don't not necessarily gases, but they can be. Right. So for example, some like carbon monoxide, carbon dioxide, well, HCl, we talked about HCl as being an acid, if you remember last time, a very strong one actually. HCl is actually, it wants to be a gas, really. I guess like it really wants to be a gas. So if you leave some, HCl out, you actually notice that it evaporates pretty quickly. So that's why they're saying HCl is a gas. So yeah, just remember that. So HCl is both a strong acid and also it tends to, evaporate into a gas. All right, now NH3. Talk about this. All right. Remember how NH3, it could be a base because it can form NH4 ammonia or ammonium. So NH3, right? You get another hydrogen, it becomes ammonium. That's why it's also a base. But yeah, it also tends to be a gas. All right, and also CH4 methane. That's in your natural gas. So that's obviously a gas. All right, so the majority though are either liquids or solids at room temperature. All right, so but a lot of them on heating, they're converted to gases much more easily than ionic compounds. So in other words, molecular compounds usually boil at a lower temperature than ionic compounds do. All right. So,
他们有个人来了，刚才那个他们不是要讲什么东西吗？
So first of all, I could kind of explain what molecular compounds are.
不是，不过他拿一个什么 speaker，所以呢，我就猜这是。
Are basically one.
他给你打电话的时候就说那个牧师要做那个什么讲话，跟
carbon
那些人嘛。
monoxide, carbon dioxide. You see, they are
你去
like
看，
an individual molecule, right? That's why it's called molecular compound because CO2
你
is
在
it's
锁车呢。
one molecule. And if you have like a container of CO2, right? If I have like a box and I filled it with CO2, then that's a lot of individual CO2s together. All right, let me just stop share for a second. And then I'll do a whiteboard, I guess. All right. So, all right. So if I have a CO2, all right, let's say that this is my CO2, all right. If I have like a container of CO2, then I'll just
他
have
拿
a
一个
bunch of
speaker， 所以
CO2.
呢，我猜是在那边。
Whatever. They kind of should be spaced more apart. Right. This is a bunch of them in a box. All right. Kind of floating around. But that's, you know, that's not the same as, how do I delete all these? All right. Here are my drawings. All right. Now, if I have ionic compound, all right, let's see. Oh, ionic compound. It's kind of like stuck together. All right, it's one piece. All right, and not only because it's solid. All right, so this would be something solid. All right, so it's like stuck together. Right, but even if it's not. All right, even if we're talking about like in liquid form, right? Or even in solid form, your CO2 not gonna be as, I guess, like uniformal as your ionic compound is gonna be. It's still gonna be a little bit loose. All right. This looseness, can you guess, you know, how this might apply to CO2 being a gas much easier than, you know, something like salt. All right. Do you guys have an idea for why? All right. All right. Let's see. So I'm talking about why like an ionic compound like this, right? Why it might be like harder to form a gas, as we said, you know, for this to be a gas, you know, let's say this is salt, right? For salt to become a gas, right? You know, for that to become a gas, that's like 800 degrees, all right? For your CO2 to become a gas, well, I'm not exactly sure what degree it is, but you know, it's very, very low. All right. That's why, you know, CO2 around us, and you don't see a lot of salt gas around us, right? So atoms are harder to separate. Well, yeah, yeah, I say that's a pretty good answer. Yes, so it is that they're harder to separate because you see, ionic compounds are actually held together really tightly, as we said. But you see, something like CO2, right? It's way easier. So because the molecular compounds, you see, molecular compounds, as we showed in the picture, right, they're kind of further apart. The atoms, or maybe not the atoms, but the molecules, right? Each molecule is itself, and it's like interacting with other molecules, but not as tightly as an ionic compound, where it's one solid piece, right? Everything is interacting strongly with others, and that's why to form a gas, it's basically separating each molecule, right? In a gas, every molecule is by themselves, and they're gonna be really far apart. And if you're starting with some molecular compound, which is already pretty far apart, it's already, being by itself, then that would be much easier than to separate an ionic compound. So that's something that we call intermolecular forces. So if you notice here that right? Inter means like international, right? It's like in between the molecules, all right? Just intra, there will be in one molecule. Right? But this intermolecular, then that means it's in between, in between these molecules, the attractive force in between these molecules. And to determine which one is stronger, well, that's basically using experience. So, if you look at an ionic compound, then you will know that, well, okay, so first of all compounds will have something called a London dispersion force. That's just something that all have. And basically the bigger, well, actually it's the more electrons you have, the stronger this force is. This force, is just the natural, kind of attraction between molecules. And basically, yeah, the bigger you are, the more attractive you are. And then the next one will be, your dipole forces. Your dipole forces has to do, well, it has to do with if your molecule is polar, right? So something like water, that will have a dipole force, and something nonpolar like methane, it wouldn't have a dipole force. So if you have a dipole force, then it will be even stronger. It will be even harder to break apart. All right, and then there's also hydrogen bonds, right? You might have heard about hydrogen bonds when you're learning about water. So all of these are intermolecular forces. But yeah, we'll be talking about some of these later. For today, just know that intermolecular forces would be, why. So yeah, I guess said this. The meeting will end in 10 minutes. Upgrade now to remove the 40-minute limit. What the? Okay. Yeah, so atoms are harder to separate. Yeah, so, I guess more appropriately, it would be actually that molecules are harder to separate. All right. So the properties of gases. So this is something that, all gases kind of have. And one of them is that gases assume the volume and shape of their containers. So yeah, gases don't have a fixed shape. They're not like solids. If you put them in a container, they'll become the shape of the container. Right. Gases are the most compressible of the states of matter. All right. So as I said, gases are basically, every single one of your molecules going to be really far apart. They're going to be very loosely connected. All right. So that's why it's extremely easy to compress them. All right. So gases will mix evenly and completely when confined to the same container. So yeah, if you add two kinds of gases, then they'll mix very fast. You don't have to, stir them around, shake them around, right? Like if you bake or cook or something, you know, have to mix stuff around. Well, you don't have to do that with gases, just dump them into the same container and they'll mix. And well, that's actually because gases are moving very fast. You don't feel air moving in a room, but they're actually moving extremely fast. They move, like they're moving at like hundreds of miles an hour, and the only reason you're not feeling them is, well, they're actually they bump into each other. They bump into things because there's so much gas and they move so fast. They actually bounce into each other and then they bounce off, and their forces are actually kind of, I guess, how should I say this? The collision, like takes away the force. All right. So that's why you're not getting penetrated by gas. But yeah, they're actually moving very fast around us. So that's why they bump into each other and then they mix very fast. So yeah. All right. So also gases have lower densities than liquids or solids. Yeah, it should make sense, right? Because they're further apart. They're when something's further apart, then they're less dense. All right. So all right. So now we're gonna be talking about pressure. So gases exert pressure on any surface with which they come into contact with because gas molecules are constantly in motion. Yep. So as I said, the gases are in motion. You don't feel them penetrating you, but they do apply a little bit of force on you, right? So yeah, the SI unit of pressure is called Pascal, PA. All right, abbreviated PA, or not abbreviated. It's like the name or the unit. It's PA. All right, pascals. All right, and a Pascal is basically 1 Newton per meter squared. That's more of a unit that physicists use. All right, if you're a chemist, next year, in your honors chemistry, all right, you're not going to be using pascals. I don't think anybody in chemistry uses pascals. Yeah, that's a physicist unit and not something that chemists want to deal with because, well, it's too difficult for chemists. No, but honestly, it's a dumb unit, and you'll probably see why a little bit later. All right. So the force experienced by any area exposed to Earth's atmosphere is equal to the weight of the column of air above it. So yes, the atmospheric pressure is the pressure exerted by the Earth's atmosphere. All right. So you have air above your head, like 9 kilometers or is it 9 kilometers? I don't really remember, but anyways, a lot of kilometers. A lot of air above your head. Actually, if you look on the third line, I wrote here that there's 14.7 pounds of pressure from the air alone on every square inch at sea level. All right, so if there's so much pressure, then why are things not breaking? All right, I think your textbook uses an example of a piece of paper. All right, a flimsy piece of paper. All right, how can you hold that out without it bending? Without it, folding. If there's 14.7 pounds on every square inch, how are you not breaking a piece of paper? Honestly, how are you staying alive? How is your back not getting broken yet? Does anyone have an idea of why that might be? All right, let's just type in chat, guys. Why am I not dying from the air pressure? All right, okay. So pressure inside is pushing outwards. Okay, that's a good explanation, I would say. Natural force. Well, what do you mean by natural force? Please, specify. What natural force? It's in physics. Oh, that's the normal force. All right. Well, it's not really the normal force, I would say. Okay, so the normal force in physics, usually that's talking about, well, the force. But usually we use it for the force opposing the pull of gravity. But yeah, so I think the explanation that the pressure inside you is pushing you outwards. I think that's a good one. So basically, air pressure, all right, it's not one way. Doesn't just happen from the top pressing you down. Actually, it's all around you. All right, it's actually all around you. If it's pushing the same from each way, then well, you're getting, and also from outside in and inside out. All right, from top down and down to up. So everything is canceling out. That's why, things don't break. If you have force from one side, then it might break. If it's all sides, then it kind of cancels each other out. So that's kind of why things are not breaking around this. And also, there's like 1 minute before the Zoom ends. I don't know why. Zoom, please. Zoom wants money. Upgrade to Pro. All right, wait. Okay. I guess we might have to go back in the Zoom. Jeez. It's never happened before. I think we have too many people here. Well, just come back in a minute later, I guess. Well, let's see. Less than 1 minute. Yeah, I think you guys might have to join back in the meeting later.